This is a brief introduction to the science of the nucleus. The nucleus, the very heart of the atom, is made up of two kinds of particles, neutrons and protons. The protons are positively charged, the neutrons are neutral, they have no charge. The total number of nucleons, that is the total number of protons and neutrons, equals the atomic mass number of the nucleus. So it's related to the total amount of mass in the nucleus. So it's the atomic mass number. The total number of protons is called the atomic number. The atomic number, the number of protons, is equal to the number of electrons that orbit the nucleus in the atom. Isotopes have the same number of protons and therefore the same number of electrons and therefore the same chemistry. The electrons determine the chemistry, but have different numbers of neutrons, so they have different atomic mass units. They have different weights or different masses. So here we're looking at carbon-12, which has 6 protons and 6 neutrons. Carbon-13 has 6 protons, of course, and 7 neutrons, and carbon-14 has 6 protons and 8 neutrons, or total atomic mass number of 14. Some isotopes are radioactive, so they decay by the emission of a particle. The 3 types of particles are alpha rays, which are actually a nucleus of a helium, a beta ray, which is actually an electron, or a gamma ray, which is a high energy photon. So when a radioactive isotope decays, it emits a particle, one of these 3 typically, and has a little change in its properties. An example of natural radioactivity is the carbon-14 isotope. This is a naturally occurring isotope of carbon that decays with the emission of a beta ray. The details of this process aren't important. It's not important to know what carbon-14 decays to, but this is a naturally occurring radioactive decay process. It turns out it's a fairly important process for determining the age of ancient organic material. Now, it turns out that the half-life for the decay process, the natural radioactive decay of carbon-14, is about 5,700 years. That means half of the original carbon-14 will decay away in that time period, leaving half of it. Then, in that equal additional time period, half of that remaining will decay away, leaving a quarter. Then, in an equal amount of time, half of that remaining quarter will decay away, leaving an eighth, and so forth. It just turns out that this timing knowledge allows us to date the age of some materials. A very different nuclear process is the fissioning of a stable nucleus. In this case, uranium-235, an isotope of uranium, is struck by a neutron and absorbs that neutron. The resultant nucleus is unstable and breaks apart or fissions into 2 daughter nuclei. Those 2 daughter nuclei are roughly of equal mass and carry away a great deal of energy that's released in this fissioning process. In this case, we see 2 particular daughter nuclei, but there are many other possibilities for that fissioning process. So the details of this process aren't important. What's important is the overall picture of this. So not only is energy released, and it's released in the kinetic energy of those nuclei, and then that energy is transmitted to the surrounding water or other medium and becomes heat in the surrounding material. And also 3 neutrons are released, and those neutrons go on to cause a chain reaction. So the overall sum of this is the fissioning process, which is induced by the neutrons being shot into this mix. That this process, this fissioning process, releases nuclear energy, but that nuclear energy turns into thermal energy. This slide illustrates the chain reaction process. When a neutron strikes a U-235 nucleus, it causes it to become unstable. It then breaks apart, it fissions, releasing energy, which ends up as thermal energy. And also it releases 3 neutrons. The slide only shows 2 of the neutrons, but there are actually 3. Those neutrons then go on to hit other nuclei, which causes them to fission, and so this becomes a runaway chain reaction. In a bomb, it's a runaway chain reaction. In a nuclear reactor, it's a controlled chain reaction. But the main point of this slide is a chain reaction. This energy is very important because the energy could either be used for producing electricity, say, in a nuclear reactor, or it could be used to be a weapon of mass destruction, as in an atomic bomb, or it could be built into a hydrogen bomb, an even more powerful bomb. To produce useful energy from a nuclear fissioning process with a chain reaction, it is necessary to control it. So that would be control fission. And the control fission process in a nuclear reactor, for example, includes control rods which absorb some of those neutrons to control the rate of this chain reaction. If there is no control and you have enough radioactive material, that is a critical mass of material, then you could have an uncontrolled chain reaction, an uncontrolled set of fission reactions causing a uncontrolled fission or an explosion. And that's, of course, what happens in a nuclear weapon of some kind. In contrast to the fissioning process is the fusion process. In the fusion process, 2 low mass particles fuse together to produce a more massive particle, and that can produce or release a great deal of energy. And so here we're looking at the fusioning process which creates energy. Fusion is actually a process used in an uncontrolled manner in a hydrogen bomb. Scientists have been working at trying to have controlled fusion, trying to have this happen. This has been going on for many years and is not yet a practical energy resource. Uranium is an essential fuel for nuclear reactors because it's fissile. That is, it can be fissioned. And therefore, uranium is used in these reactors. Uranium must be found, and it's found in the mining process. It's produced in a mining process. So here we're looking at a uranium surface mine where uranium ore is extracted, and then uranium is extracted from the ore. There are 2 main uranium isotopes. One we've already looked at, which is U-235, and that's the fissile. It's a fissile isotope. And the other is a more massive, slightly more massive isotope, U-238. U-238 is not fissile. When it's bombarded, it does not split into 2. It does not release energy, so it's not a fissile material. So U-235 is the material that nuclear reactors use because it's fissile. When U-235 fissions, it produces 2 reaction products, or daughter nuclei. These daughter nuclei have less mass than U-235. In this example, the 2 daughter nuclei. The two reaction products have masses of 90 and 143 respectively. And also there are neutrons produced which participate in the chain reaction. So this is one of several different processes of U-235 fissioning which occur. When we mine uranium, the material, the uranium we extract from the uranium ore is mostly U-238. U-238 is the isotope of uranium which is not fissile. So there's only a small amount of U-235, the fissile isotope. There's only 0.7% of all the uranium we extract in the mining process that's actually useful for radioactive fissioning. And so we need to do something about this. We need to be able to enrich that uranium so that we have more U-235. To be useful in a nuclear reactor, uranium needs to have a concentration of around 5%. So somewhere we have to take uranium, which naturally only has U-235 and a concentration of 0.7%, and you get that U-235 concentration up to around 5%. If we wanted to make nuclear weapons, we'd have to get the concentration of U-235 much higher, up around 90%. So somehow we have to separate U-235 from U-238. We cannot do this chemically because U-235 and U-238, remember, they have the same number of protons, they have the same number of electrons, therefore they're chemically identical. So we have to find some way to separate them out, and we have to have that separation based on their mass difference. So somehow we have to use the fact that U-235 has a lighter mass than U-238, the heavier mass non-fissile material. One of the enrichment methods that we use is called gaseous diffusion. And this, we basically let the uranium, we make the uranium into a gas, we let it diffuse. The heavy U-238 is less likely to be able to diffuse rapidly, and the less massive 235 diffuses rapidly. Therefore, we can separate them out using that method, and we can see the little green dots in this diagram are supposed to represent U-235. We can enrich the gas because we can get the diffusion product U-235 coming through the permeable membrane first. Another method that can be used to enrich uranium, that is, produce more U-235 concentration, is called the gas centrifuge. In this case, we take uranium, which is a gas, which has been made into a gas, put it inside a centrifuge, spin the centrifuge. The heavier U-238 goes to the outside, the less massive U-235 goes to the center. We pull off the U-235 from the center, and we get a more enriched, that is, more U-235 gas coming off the center. So that's gas centrifuge, another way to enrich uranium. Once we have enriched uranium up to around 5%, that is, it's 5% of uranium now is U-235 rather than the naturally occurring 0.7, then we can use that uranium for fuel for a nuclear reactor. We can make it into fuel rods. We wanted to make a nuclear weapon, we would have to enrich that material to a much higher fraction, to was almost all uranium-235. That's a more difficult process, and that's one of the reasons why countries like Iran have so much trouble producing nuclear weapons, is that enrichment process is a very difficult technical process.